let us first discuss a central quantity for any dispersed two-phase flow, which is the Stokes number. It is defined as the ratio of a relaxation time to a flow timescale T-flow. As you can see, the relaxation time is only affected by the physical properties of the fluid particle system. In contrast, the flow timescale depends on a specific situation. It is defined by a length scale of the flow, L flow, as well as the flow speed U. Defining this flow timescale can be a bit tricky, but some intuition should help us to do this. Once a Stokes number is calculated, we have a powerful quantity in the hand. The reason is that the Stokes number is the key criterion to decide on the necessity of coupling. Specifically, if Stokes is not too small, we will call this the perfect coupling limit, and not too high, i.e. the no coupling limit that we will detail in a second. CFD-DEM coupling makes sense. Let us have a closer look at these limits now. First, this is the low Stokes number limit, i.e. the phases are very tightly or perfectly coupled, such that we can speak of a perfect coupling and hence particles will move with the fluid. Also, in such applications there is often a homogeneous distribution of particles in the simulated domain, originating from turbulent fluid motion or particle diffusion. Due to the tight coupling, particles have no or only a very low slip velocity relative to the fluid. As the definition of the Stokes number implies, this is the case for small light particles, highly viscous fluids, and large flow distances L flow. For example, an impinging flow in which particles flow with a gas through a nozzle onto a plate, we have the relevant length scale as half the jet diameter. If now the jet diameter is large and the jet velocity sufficiently small, particles may only insignificantly move relative to the fluid when flowing through the nozzle. Imagine, for example, dust particles or nanoparticles suspended in air flowing through such a nozzle. Clearly, we would anticipate they will simply move with the gas and nothing surprising will happen. The other relevant limit is the high Stokes number limit, for which no coupling to the fluid is necessary. The simple reason is that the fluid interaction forces are not relevant and the deflection of the particles is only insignificant due to the fluid motion. Again, considering our jet example, this would mean a fast flow and large particles with a high density. Also, imagine that the fluid has a low viscosity because, for example, vacuum is applied and the nozzle has a small diameter, resulting in small flow distances L flow. Consequently, the fluid will rapidly change direction, i.e. T flow is small, and hence particles have no chance to change their direction when moving through the nozzle. Examples in which this no coupling limit is relevant include centimeter-sized tablets in a coater, granular jets impinging on a surface, droplet sprays, or crushers and mills that operate in a dry mode. Once we have understood the necessity of performing CFD-DEM simulations, we can move on to the next point in the decision tree, namely how detailed we need to perform the coupling. Option 1 is the so-called one-way coupling, which is illustrated here on the left. The particle will not alter the flow, but might have a trajectory that deviates from the streamlines of the fluid, nothing else. Such a coupling strategy is adequate for both low mass loadings and low particle volume fractions phi-p. One-way coupling means that only particles see the fluid, but no other interactions, e.g. the effect of the particles on the fluid or particle-particle collisions are accounted for. Since particle mass loadings are small, fluid turbulence might be important, and hence it is typical for these applications that the fluid's fluctuating motion is modeled in some way, e.g. with a stochastic algorithm that aims at predicting the local fluctuating velocity. A key issue with one-way coupling that cannot be easily overcome is the fact that Newton's third law is conflicted. Thus, the coupling algorithm does not conserve the momentum of the mixture, but introduces a global momentum error. This is why nowadays very often two-way coupling is performed, which is illustrated in the right panel here. Two-way coupling allows the modeling of higher mass loadings, but still at particle volume fractions being low, e.g. less than 0.02. Also, this coupling approach allows that also the fluid sees the particles, such that both phases have a realistic interaction with each other. Particle-particle collisions are either not or only in a strongly simplified way accounted for. As already stressed, the important thing is that two-way coupling respects Newton's third law, although it is not always strictly enforced. We will see that the details of the particle-to-fluid coupling algorithm are important, whether Newton's third law is precisely enforced or not. More on this later. A more exotic wording found in literature is that of three-way coupling. It is only rarely mentioned. The reason is that the two-way coupling approach already accounts for a key effect, which is that particles indirectly affect each other via the motion of the fluid. The ultimate coupling approach is four-way coupling, which is realized by all available CFD-DEM models and is illustrated in the right panel. This way of coupling gives us full freedom of the application of a CFD-DEM model, meaning that it is also useful in high mass loading and high particle volume fraction applications. The motto of four-way coupling is everyone sees everyone, meaning that particle-particle collisions and particle fluid and vice versa effects are accounted for. Typical is also that detailed collision models are used. Very often soft sphere DEM is preferred over hard sphere DEM for reasons already discussed in earlier units. Of course, also Newton's third law can be respected and sometimes can be even enforced. As we have now also decided on the details of the coupling, we can progress to the next important detail of our CFD-DEM strategy, which is the fundamental question: shall we resolve the fluid flow around the particles or not? In case we want to do this, we call this the particle resolved or fully resolved approach, which is nicely illustrated here in the figure provided by Weinhardt et al. As you can see, when following such an approach, the CFD mesh has to be finer than all the considered particles such that small-scale flow features are resolved. The force acting on the particles can then be directly evaluated from the stress and pressure field in the fluid. Next, there is the rarely used option of a semi-resolved flow approach. As seen in the center panel, only large particles are resolved with the CFD mesh, while smaller ones are not. This approach is computationally rather complex, since the simulation tool has to decide which particle is resolved and which not. This already brings me to the unresolved approach, which is called the averaged volume method, or AVN, in some literature references. The reason for this naming is that none of the particles are resolved by the CFD mesh, and particle information is averaged over individual mesh volumina. This requires closures for the fluid-particle interaction forces, for example the drag force, which are necessary to make reasonable predictions. The CFD results, specifically the pressure and velocity, are an input to these closures and are not directly used to evaluate fluid-particle interaction forces as in the resolved approach. Also, I want to mention a specialized form of this unresolved approach, which is the unresolved parcel approach. This approach has been nicely documented, for example by Osel et al., and has a wider applicability than the classical unresolved CFD-DEM approach, specifically to larger systems. However, it also has a lower predictive power, since certain assumptions about the parcels have to be made. The next slide illustrates the differences between the resolved in the left panels and the unresolved in the right panels approach for coupling. Clearly, the resolved approach typically relies on a local grid refinement to keep the computational cost reasonable. Unresolved often uses structured grids with identical cell size to keep things simple. This set of figures illustrates the corresponding results for the fluid velocity. Note that fluid flow is from the bottom to the top and that the particles do not move in this simulation. Hence, in the particle resolved approach, the speed inside the particles is zero, while this is not the case for the unresolved approach. You see, we have here a fluid velocity which is a result of this averaged approach. Clearly, local velocities are very different, as well as we see the formation of streaks behind individual voids in the particle bed in case we use the resolved approach. We now progress to another important detail of the flow prediction, namely the temperature and heat flux distributions. Specifically, we focus on the time evolution of these quantities associated with the three particles that are colored here in red and that are located near the center of the bed here on the top. The black line is associated with the axis on the right hand side and illustrates the particle temperature. As you can see, the particles are heated up and reach a peak temperature of approximately 1000 Kelvin. Note that the shaded area in this figure depicts the min-max range of the particle temperature and the heat rate. Interesting is the axis on the left. You see the convective heating rate in red, which has a peak of approximately 1.5 watt, and the radiative heat that peaks around 5.1 watt. As can be seen at the top, this is the result for a particle resolved approach, and we will compare this now with the results of an unresolved CFD-DEM simulation, as shown here on the right. Clearly, the temperature evolution in black is quite similar. However, the exchanged amount of radiative heat is greatly underpredicted compared to the resolved simulation. In contrast, the convective heat transfer rate, here in red, differ between these two particle approaches, however, not substantially. This work of Jäger et al. Nicely illustrates situations in which particle resolved simulations should be favored, namely in case radiation becomes the dominant heat transfer mode. Let us finish our resolved or not chapter with another heat application, the cooling of a sphere via a fluid flowing past it. The fluid will flow from the top to the bottom in what we will see, and we look at dimensionless temperature profiles. Both the fluid and the particle domain are fully resolved, meaning that we used a two-region solver in the software package OpenFOAM. What we see here specifically are two spherical particles, but with different particle conductivities. On the left, a higher conductivity, and on the right, a much lower one. As you can see, the temperature inside the particle is more homogeneous on the left. Please note that temperature scales are very different. Also, you see that the temperature distribution is not perfectly symmetric. The temperature at the nose is a bit lower in both cases. We can cast the problem in dimensionless quantities, which are the Fourier and Reynolds number, which are not shown here, as well as the very important Biot number, defined here on the very right. The key message is clear. High Biot number applications may require a resolved approach, not only of the fluid domain, but also on the intraparticle level, meaning inside the particle. The reason is the inhomogeneous temperature distribution inside the particle.